Hello all, welcome to this video on Networking Lab. Today I'll be talking about Go Backend ARQ protocol and its implementation in C. To improve the efficiency of transmission, multiple frames must be in transition while waiting for an acknowledgement. We need to let more than one frame be outstanding to keep the channel busy while the sender is waiting for an acknowledgement. In the Go Backend protocol, we can send several frames before receiving acknowledgement, and we can also keep a copy of these frames until the acknowledgement arrives. Now let's look into the sequence numbers. Frames from a sending station are numbered sequentially. However, because we need to include the sequence number of each frame in the header, we need to set a limit. If the header of the frame allows m bits for the sequence number, then the sequence numbers range from 0 to 2 raised to m minus 1. For example, if m is 4, the only sequence numbers are 0 through 15 inclusive. However, we can repeat the sequence. Now we'll look into the sliding window concept. It is an abstract concept that defines the range of sequence numbers that is the concern of the sender and receiver. The range which is the concern of the sender is called the send sliding window. The range that is the concern of the receiver is called the receive sliding window. And in each window position, some of these sequence numbers define the frames that have been sent. Others define those that can be sent. And the maximum size of the window is 2 raised to m minus 1. The window at any time divides the possible sequence numbers into 4 regions. The first region from the far left to the left wall of the window defines the sequence numbers belonging to frames that are already acknowledged. The sender doesn't worry about these frames and keeps no copy of them. The second region defines the range of sequence numbers belonging to the frames that are sent and have an unknown status, which is given in the orange color. The sender needs to wait to find out if these frames have been received or were lost. We call these outstanding frames. The third range defines the range of sequence numbers from frames that can be sent. However, the corresponding data packets have not yet been received from the network layer, which is given in the yellow color. Finally, the fourth region defines the sequence numbers that cannot be used until the window slides. Now let's look into the receive window. The receive window makes sure that the correct data frames are received and correct acknowledgement are sent. Size of the receive window is always 1. The receiver is always looking for the arrival of a specific frame. Any frame arriving out of order is discarded and needs to be resent. Here only one variable will be used, which is given by Rn. The sequence numbers to the left of the window belong to frames already received and acknowledged. The sequence numbers to the right define frames that cannot be received. Any received frame with a sequence number in these two regions are discarded. Only a frame with the sequence number matching Rn is accepted and acknowledged. The receive window also slides, but one slot at a time. When a correct frame is received, the window will slide. Now let us look into timers used. Although there can be a timer for each frame that is sent, here only one will be used. The reason is that timer for the first outstanding frame will always expire first. We send all the outstanding frames when the timer expires. Now looking into the acknowledging and resending of a frame. The receiver sends a positive acknowledgement if a frame has arrived safe and sound and in order. If a frame is damaged or received out of order, then the receiver is silent and will discard all the subsequent frames until it receives the one it is expecting. The silence of the receiver causes the timer of the unacknowledged frame at the sender's site to expire. Now, this in turn causes the sender to go back and resend all the frames beginning with the one with the expired timer. The receiver doesn't have to acknowledge each frame received. It can send one cumulative acknowledgement for several frames. Now, regarding the resending of a frame, when the timer expires, the sender resends all the outstanding frames. Now, let us look into the design of go back and ARQ. Now, the idea is similar to stop and wait ARQ. The difference is that the send window allows us to have as many frames in transition as there are slots in the send window. In the go backend protocol, the sequence numbers are modulo 2m, where m is the size of the sequence number field in bits. The send window is an abstract concept of defining an imaginary box of size 2 raised to m minus 1. Like the receiving window, the sender window also has variables. Now here we have three variables: SF, SN, and S size. Now, the send window can slide one or more slots when a valid acknowledgement arrives. The receive window is an abstract concept defining an imaginary box of size 1 with one variable, which is Rn. The window slides when a correct frame has arrived. Sliding occurs one slot at a time. In go back in ARQ, the size of the send window must be less than 2 raised to m, and the size of the receiver window is always 1. Now, this is a diagram depicting the design of go back in ARQ. Now, as discussed in the previous slide, we will see why the size of the send window must be less than 2 raised to m. Now, this figure here compares the window size of 3, and the next slide compares the window size of 4. Now, when we see the case where the window size is 3, and we assume that all the 3 acknowledgements are lost here. So, the frame 0 timer will expire and all these 3 frames will be resent. The receiver is actually expecting 3 now and not frame 0. So, the duplicate frame is correctly discarded here. On the other hand, we'll take the case where the size of the window is 4 and we again assume all the acknowledgements are lost. So, the sender will send a duplicate of frame 0. However, this time the window of the receiver is expecting to receive the frame 0. So, it accepts the frame 0 not as a duplicate but as the first frame in the next cycle. Now, this is an error. Now, let us look into the efficiency of go back n protocol. Now, that is given by n by 1 plus 2a, where a is given by Tp by Tt. Now, Tp is the propagation delay and Tt is the transmission delay. Tt or transmission delay can be given by d by b, where d is the data size and b is the bandwidth. And the propagation delay Tp can be given by distance by the wave propagation speed. Now we'll calculate the effective bandwidth or throughput of go back in. Now, throughput is the number of bits per second transferred between two stations in the network. It is the maximum bit rate for a given packet size. Now, effective bandwidth or throughput can be given by efficiency multiplied by the bandwidth. So, effective bandwidth can be written as n by 1 plus 2a the whole multiplied by b. Now, we'll look into the utilization factor here. Now, the pipeline protocols are an improvement over the stop and wait protocol. To achieve better network utilization, we have multiple frames in flight between the sender and the receiver at a given time. N denotes the window size and go back N, which the sender is allowed to send before receiving an acknowledgement. Basically, if N is 1, then we have a stop and wait implementation. Now, utilization is the ratio between the actual and the maximum network throughput. For a fixed packet size or a constant bitrate stream, lowering the utilization will increase the inter-packet gap. Therefore, the maximum possible link utilization formula, disregarding any overhead, can be given by utilization which is less than or equal to n by 1 plus 2 into BD. Now here, BD is the bandwidth delay product representing how much data can be carried over the link at a given time. It is calculated as the data link's capacity multiplied by round trip delay time. Theoretically, we find the maximum possible n by solving the equation we saw before for utilization equal to 1. However, in practice, we need to use an even smaller value for n. Now, there are two main reasons for this. The first one is that we need to consider at which rate the receiver can process the packets arrived, as well as having a high network utilization. If the receiver cannot cope up with the processing of the packets, it will drop them. In this case, the sender will be retransmitting the same packets over and over again. The successfully transmitted package rate will be inadequately low. Hence, achieving high utilization is meaningless. Now, the concept of preventing a fast sender from drowning a slow receiver in data is called flow control. Flow control enforces a smaller window size n concerning the receiver's processing speed. Now, the second reason is that, though equally important, is to limit the window size n is congestion control. Too many packets being present in or a part of the network can cause packet delays and packet losses, which can degrade the performance. Indeed, a sender should respect each element in the network so that the overall network performance is utilized. Now we look into the algorithm for the sender side. As we already saw, there are three variables that are concerning the sender window. So the first one is the size of the window, SW, which is 2 raised to m minus 1. And SF is the send window's first outstanding frame. So that is currently 0. SN is the send window, that is next frame to be sent. That is also 0 when the program is starting. So while true, the sender will be in a wait state. And if there is an event happening called send request, what happens is it will check if SN minus SF is greater than or equal to the window size. If it is so, then it will go into a sleep state. It will get the data. It will make the frame, store a copy of it until it's acknowledged, and it will send that frame to the receiver. And it will increment the value of Sn. Now, if there is no timer running currently, then the timer will be started. And if the case of event is such that an acknowledgement is arrived, then it will receive the acknowledgement. And if the acknowledgement is in a corrupted state, what it does is it will go into a sleep state. It will also do a comparison that if the acknowledgement number received is something less than SF, and if the acknowledgement number is greater than if the acknowledgement number is greater than SF and if the acknowledgement number is less than or equal to SN, and if still the number is less than or equal to SF, then what it does is it will remove the frame SF because we have received the acknowledgement for it, and SF will be incremented by 1. It will slide forward and the timer will finally stop. And if the event is timeout, which means the timer needs to be restarted, and to a temporary variable we will store SF because that is to be resent. So if we are checking if the value of SF is still less than SN, we'll keep on sending the frame SF and it is increment after sending. Now looking to the algorithm at the receiver side, there is only one variable, so Rn will be equal to 0. While the loop is true, it will wait for an event. So if the event occurring is an arrival notification, then it will receive the frame and it checks the frame. If it is corrupted, what it does is it will go to a sleep state. Yes, a retransmission will happen from the sender side and it will check the sequence number which has been received with the Rn, that is the frame which you are waiting to arrive. If both of them are equal, then the data is delivered. Rn is sliding by 1 and an acknowledgement for Rn is sent to the sender. Now we look into the functions and header files that are used for the program done as sender. So the std library.h will be used and the function exit inside it will be used to cause a program termination normally. So the status code we are giving here is 0. Then we have included another header file called sys/socket.h. From it we are using the function bind. So what bind does is it will assign the address that is specified by the socket to the socket that is referred by this file descriptor. Then we have another function from the same header file, accept. So what it will do is it will extract the first connection request from the queue of pending connections which is there for the listen function. So in the listen function, the second argument is a queue of connection request. So it will extract the first connection request and then it will create a new connected socket and then return whatever value it is as int. Then we have the listen function which is used for accepting incoming connection request. So it will act as a passive socket. Then we have the socket function. It will create an unbound socket. So it will specify the domain, the type of socket and the protocol used, and this socket will be later used for different operations. So it will return a socket descriptor. Another header file used is netinet in.h. From that we'll use this structure variable sudder, which is an unsigned integer of 32 bits. Then we use this sockadder structure which stores the address of the internet protocol family used. Then we have another header file which is unisted.h. From that we use the read function. So it will read these many number of bytes from the file descriptor into the buffer. Write will write a specific number of bytes from the buffer to the file referred by the file descriptor. Then we have the close function that is used to deallocate the file descriptor. Then we have a sleep function which will suspend a called process for a specific amount of time that is given as the argument here. Then we have arpa inet.h which contains a function called htones that will convert the given argument from host order to network byte order. Then we have the header file stdio.h. From that we use the printf function to print the formatted output to the standard output and scanf to read data from the standard input and then write the result into the arguments given here. Then there is the string.h header file. From that we use the function memset. Memset will copy the argument given here to each of the bytes of the object pointed by this pointer. Then we have string copy for copying a string pointed to into an array pointed to by this pointer. Then we have the string length. It will compute the number of bytes of string without including the null byte. Then we have systime.h. From that we will be using the concept of file descriptor set. fd underscore set is a bit array that is representing a file descriptor set. Now we have a macro called fd set. What it does is it will add the file descriptor given to the file descriptor set represented here. Then we have a macro called fd0. What it does is it will initialize the file descriptor set as empty. Then we have a function called select. Now this function will block the calling process until there is activity in any of these specified set of file descriptors. So this is the set of read file descriptors, this is the set of write file descriptors, and this is the set of exception calling file descriptors. So if any of these have an activity going on, or if the timeout period has expired, it will check only the first NDFS number of file descriptors. So the timeout can be specified by the user using this structure, and also the value of NFDS will be equal to the total number of file descriptors plus 1. It acts as a limit, the limit to which the file descriptors need to be checked. Now the normal return value will be the total number of ready file descriptors in all the sets. Now if the select is returning because of a timeout, then that will be 0. If an error occurs, then the return value will be -1. Then we have a structure time underscore t, that is a time value structure where the time can be specified in the form of seconds or microseconds. Now we look into the functions and header files that are used in the receiver side. Now we begin with stdlib.h, the same function we saw in the sender side also, the exit function. Then from the sys/socket.h we have the connect function. So that is used to request a connection to be made onto a particular socket. Then we have the socket function which we already saw. Then netinet/in.h, we used the same structures in sender side also. Then from the string.h we have memset and string copy and string length, the read function from unisted.h, then write function, sleep function, and close function. From arpa/inet.h we have htones, we already saw that before, and we also use another function called inet_adder. Now this will convert an IPv4 address from a string into a dotted decimal representation to an integer. Then from stdio.h we'll use the printf and scanf functions. Now we look into the three cases of transmission that we are considering here. The first case is when the send and the acknowledgement is received and all of it is a success. So here initially we are sending frame 0 and frame 0 has been acknowledged and acknowledgement is sent for the next frame, which is 1. It was received successfully here and the window slided by 1 position to the right. So that is a successful case of send and acknowledgement. Then we have the second case where there is a loss of frame. So here we assume that frame 1 was lost. So there was no indication from the receiver that any kind of loss happened. So what it does is it will keep on sending the frames in the window. So frame number 2 is send. Frame number 3 is also send. After the sending of frame 3, the timer of frame 1 has expired. So it will restart the timer. So until now, no acknowledgements have been received from the receiver side. So what it does is, it will again resend the outstanding frames, that is the frames which were sent but whose acknowledgement wasn't received. So we are resending frame number 1, then we are resending frame number 2, and each of them is acknowledged and the window is sliding by 1. And then we are sending frame number 3, it is sliding again. So then we get the acknowledgement for the next frame, which is frame 0. Now this is an example of a cumulative acknowledgement. You can see that we don't have an individual acknowledgement for every frame sent. So in go backend, you can have either an individual acknowledgement or a cumulative acknowledgement. So this cumulative acknowledgement meant that all these 3 frames were received successfully. So that is why the window has gone to the right by 3 positions. Now we'll look into the case of an acknowledgement loss. Now here frame 0 is sent, acknowledgement received to send frame 1, frame 1 is sent. Suppose the acknowledgement to send frame 2 was lost. The sender will keep on sending the next frame 2, then it will send the next frame 3. After receiving 3, the receiver is sending an acknowledgement for 0. So in case of this individual acknowledgement loss, this cumulative acknowledgement is taken into consideration. So there need not be any extra acknowledgements that has to be sent, like in the case of where the frame was lost. There is no resending of any acknowledgement here. Now this is the demo transmission that will be you doing using the program here. Now we have the window size as 7 for the sender and 1 for the receiver. So total will be 8. So the sequence number range will be from 0 to 7. Now we send frame 0, then we are sending frame 1, and here we have modeled a cumulative acknowledgement asking for frame 2. Then we send frame 2. We are giving an individual acknowledgement for receiving frame 3. Then we send frame 3 and frame 4. Then we get a cumulative acknowledgement to send frame 5. And the next frame number 5 is assumed as being lost. Then it was not informed to the sender, so it keeps on sending the next frame, which is frame number 6. Then the timer of frame 5 is expired. And also this frame 6 wasn't something that the receiver was expecting. So it will discard it because it was received out of order. So the sender will resend the packets 5. So the receive window will slide by 1. Then it sends 6. The receiver will again slide by 1. And a cumulative acknowledgement is sent for receiving frame number 7. And so on it goes. Now we look into the program for Go Backend server, which is modeled as the sender. We have included all the header files and we have created a set of file descriptors in the sender side or the server side. Then we call the function socket. Communication domain is local communication, sock stream, and the default protocol is 0. This is a TCP socket. That's why we gave it as sock stream. Then we are clearing the memory, filling it with zeros for these two structures. Then we are defining the sock header structure, internet family. So SIN underscore family will be the address family AFINet. then SIN underscore port will be converting the port in the argument here, that is 7004. We already saw the function htones, which is used for converting the host byte order to the network byte order. Then we have this argument sin underscore adder dot s underscore adder. So this will mean that the server can accept connection from any of the clients which is asking for a connection request. Then we have the bind function. Then servers listening for the connection request. Then it will accept the connection. Then we are going to a section where we are modeling the communication between the sender and the receiver. So there is a label 0. What it does is it will clear the write buffer, write the message to be sent to the receiver to the buffer, and then it will write the content in the buffer to the corresponding descriptor. Now we have the next label. The same steps are repeated where the buffer is cleared. Then again the data to be sent to the receiver is set and written to the corresponding file descriptor. Then what we do is we'll create the file descriptor set that is given here, and we'll add different file descriptors to this set and will set the bits for this file descriptor. Then we are setting the timeout as 2 seconds. Then we use the select function. So for return value being -1, we say there is an error. Or if the return value is 0, it means that the timer has expired. Timeout event has happened and the corresponding steps will be done. And if the return value is something other than these two cases, what we do is we'll use the read function to read data from the file descriptor and write it to the buffer. So that is data from the receiver to the sender. And we'll print it to the terminal. And finally, after all the communication is done, both the socket descriptors are closed. Now looking into the program for go back client or the receiver side, some of these steps are similar to that of the server. We include the required header files and we clear the structures, then set up the internet address family, and the socket is created, after which we'll call the, this is the socket creation, we call the connect function. Connect will send the connection request to the server. Then we have a loop where the read buffer is cleared each time and write buffer is also cleared. And what it does is it will keep on reading the read buffer to see if any data has been transmitted from the sender side. If at all there is some data in the buffer, then that is printed out. After all that, if some data has to be sent from the receiver to the sender side, it will be written to the write buffer, and that will be written to the file descriptor using the write function so that the sender can read it using the read function there. Finally, we'll close the socket used. Now this is a screenshot of the output at the sender side or the server side. Here the window size of go back n is, the n value will be 7. Then we send frame 0, frame 1, which was the demo transmission I had discussed before. We get a cumulative acknowledgement 2, and for 3 we get an individual acknowledgement, when then we send 3 4 and we get acknowledgement 5, which is a cumulative. Then we send 5, we send 6, but 5 frame has been lost. Then it goes into a timeout because 5 is lost. Restarting the timer, then resending the packets 5 6, we get a cumulative acknowledgement for 7. Then we send 7 and we get an individual acknowledgement to send the next frame, which will be frame number 0. Now this is the receiver side, same thing. So here, since the packet 5 is lost, we received 6 though, but 6 is received out of order, so that will be discarded. So again, when we resend 5 and 6, they will be accepted in that particular order by the receiver side. Now we'll look into a demo of the same. Now here we have two files, go back client and go back server. And we have already discussed the program for both of them. Now we'll run the programs. Before that, we'll compile to see if there is some kind of error in it. So we compile and run the go back server program. Next, we'll compile and run the go back client program. Now this was the output. The screenshot we already saw as output of the sender and the receiver side. That's all for now. Thank you for watching.